I think we should start. So welcome back. I am Fernando Martin from Autonomous University in Madrid, and it's my privilege to introduce Anne Lullier. So for those who don't know her, because you are young, and so probably you didn't hear too much, so I will tell you who is the speaker you will face in the next an hour and a half. So Anne Lullier studied physics and mathematics at the École Normale Supérieure in Fontenay-aux-Roses. This is near Paris in France. And she got a double master degree in theoretical physics and mathematics. But for her PhD, she switched to experimental physics at the French Commissariat à l'énergie atomique, CEA, in Saclay. And she got the PhD degree in 1986 at the Université Pierre-Marie Curie for her work on multiple ionization in intense laser fields. Then she spent some postdoctoral time in Gothenburg, Sweden, and in Los Angeles. And for several years, she worked in Saclay. But in 1994, she moved to Sweden, where she started as an associate professor at Lund University, and she became full professor in 1997. There, she has established one of the leading groups in attosecond science that is well known all over the world. And she has pioneered some of the language that is currently used in attosecond science. And I will not describe in detail her scientific achievements. I would like to focus only on two of them. So the first one is together with Philippe Balcou. She pioneered the observation of high-order harmonic generation in rare gases, a technique that is nowadays used in all attosecond science laboratories. And this was published in 1993. And she's also co-author of one of the most popular and most cited papers in attosecond science that probably you have already read. The title is Theory of High Harmonic Generation by Low-Frequency Laser Fields. This was published together with Maciek Lewenstein, Philippe Balcou, Misha Ivanov, and Paul Corkum. So I'm sure you recognize all those names. So this paper has established the foundations of modern attosecond science. And it was published in Physical Review A, which nowadays, is called a specialized journal. And, well, it is a specialized journal, but this paper has got more than 3,500 citations so far, just to give you the relevance of this. So only for these two scientific achievements, she should be in history of attosecond science for sure. But it was only the beginnings of her career. She has published many more papers and has contributed enormously to this field. And you may wonder why I'm here introducing her. Well, I had the privilege to collaborate with her in 4 papers to image electron dynamics in atoms and molecules. Of course, I was responsible for the theory part, but with her background in theoretical physics and mathematics, I'm sure that it's something she could have done by herself if she had had the time to do it, or the students to do it. So, of course, she has got a number of awards that I will not describe in detail. Let me just mention a few ones. So Anne Lullier has belonged to the Nobel Committee for Physics between 2007 and 2015. She's member of the Swedish Academy of Sciences. She has received the Julius Springer Prize. In 2011, she received a UNESCO L'Oréal Award. In 2013, she was awarded the Carl Zeiss Research Award, the Blaise Pascal Medal, and a honorary degree at Université Pierre-Marie Curie. She has been elected as a foreign associate of the American National Academy of Sciences. This was in 2018, etc., etc., etc. The last prize I am aware of is the European Physical Society Prize for fundamental aspects of quantum and optics, which was awarded to her last June. So I think I should stop here. Yes. I think you have a great opportunity to learn from one of the discoverers of attosecond science, what it is, and where this is leading us in the near future. So Thank you very much, Anne, for accepting to come, and I give you the stage.
Well, thank you very much. Can you hear me? Yes? And thank you, Fernando, for a great introduction. So in this tutorial, I would like to introduce this field of attosecond science. This field, actually, I would like to correct a small thing that Fernando said. The first high-order harmonic spectra were obtained already at the end of the 80s, 30 years ago, in two groups. In the group of Saclay, and I was part of this group in '88, and also in the group of Charlie Rhodes in Chicago. And what happened then was that the subject of research was to study the interaction of atoms in a gas with intense laser pulse, and looking at the light that was emitted along the propagation axis and analyzing the radiation, we discovered that we obtained many high-order harmonics of the laser field. As you can see on this plot here, this is not one of the first spectrum, it's a later spectrum, but I think it's a beautiful spectrum showing the intensity of the high-order harmonics as a function of photon energy. And you see this beautiful plateau here. This is from harmonics 21st to harmonics 53rd, obtained in neon gas, and with all these high harmonics with approximately the same intensity. This is called the plateau of the high harmonic spectrum. This plateau is finishing with a cutoff, which I will describe later in more details. The decrease that you see at low photon energy is simply due to the efficiency of the grating, which is decreasing. So immediately after this first result came the question, are these high-order harmonics phase-locked? Do they lead to attosecond pulses of radiation? And just to explain the idea, assume that you have a number of waves, a number of harmonics, and assume that they are phase-locked, which means they are all in phase at a certain time. And because of the periodicity of the process, they will be in phase again at later time, periodic times. And if you simply sum these waves, you find that you have constructive interference when they are in phase, destructive interference otherwise. So if you take the square of this electric field, you see that you confine light into very short time intervals. And this was realized by actually several peoples, including Ted Hensch and Steve Harris in '93. And here is a quote from their article, which was really a visionary quote. If the harmonics are appropriately phased, this bandwidth corresponds to temporal pulses of the order of 5 times 10 to minus 17 seconds, 50 attoseconds, and thereby motivates a search for a new regime of short pulse generation. So this was 92, 93. So the question is, are these harmonics phase-locked? Are they in phase? What do you think? I guess they are a little bit, otherwise I would not be here. And the answer was given also in '93, both by a numerical calculation by Ken Schaefer and Ken Kullander, and by an interpretation by the same authors and Paul Karkum. And here is a presentation of this work. The numerical calculation consisted in simply numerically solve the Schrödinger equation for an atom in an intense laser field, and this is for a Coulomb potential, just to be simple. And this is the effect of the laser field. And the problem is that this is an intense laser field. Both contributions are comparable, so you cannot use the usual perturbation theory to describe the interaction with the laser field. You have to solve this Schrödinger equation, considering both contributions as comparable. And this is a picture, and now this is the picture of the Coulomb potential, which is bent by the laser field, which is represented here in the dipole approximation by a straight line. And you see that at a certain time, there is a probability for an electron to tunnel through the barrier. And what you see here is a picture from one of these first numerical calculation of the electron wave packet, which is driven away from the atom. And a bit later on, so the electron is moving out, but then it's coming back because the laser field change of sign. And there is a certain probability that the electron recombines back to the ground state and liberating its energy in the form of XUV radiation. And this is the picture of the electron wave packet coming back. You see actually lots of interference, which really indicate that this is a coherent process. The electron is recombining with itself in the ground state. So this picture has been called the three-step model, and it gives really a very intuitive picture of this process. So, as I said, the electron coming back gives rise to attosecond pulse, because all the different frequency components making this electron wave packet are more or less in phase. So this is the answer to my question. Are the harmonics phase locked? More or less, not quite, and we will go to some detail of this question later on. They are not perfectly synchronized, but synchronized enough to the creation of these short attosecond pulses. Okay, so now I showed you a generation of attosecond pulses, but I started by talking about high-order harmonics. So where are the high-order harmonics? Well, this process, which I just described, happens actually twice per laser cycle, on one side and on the other side, and gives rise to a train of attosecond pulses, which are separated by half the laser cycle. And you can notice that there is a sign flip between consecutive attosecond pulses, which come from the inversion symmetry of the problem. You have the laser field change of sign between two half cycles, and the attosecond pulses also change of sign, which leads to this train of attosecond pulses. So now if you go into the frequency domain, you make a Fourier transform and square, what do you obtain? Well, you obtain a spectrum of high-order harmonics. These high-order harmonics are separated by 2 omega, corresponding to half the laser cycle, and these are odd order of the laser field. So we only see odd harmonics. Again, related to this inversion symmetry of the problem and this sign flip between consecutive attosecond pulses. So I have here described the generation of these high-order harmonics as interference of attosecond pulses. The physics is really in the time domain. This is completely equivalent to the picture which I gave at the beginning, that attosecond pulses are sum of more or less phase-locked high-order harmonics. So I also showed here some black harmonics. This is harmonics generated above the ionization threshold, but you have also a few low-order harmonics which can be understood more traditionally with low-order perturbation theory, leading to generation of third, fifth, seventh order. Moving on this little bit historical perspective on the field, the idea of attosecond pulse generation was raised already in 92, 93, when people start to understand the process of high-order harmonic generation. But it took 15 years to really show in the laboratory that indeed we had attosecond pulses. So this was realized in 2001. And it was realized at the same time, more or less, both for attosecond pulse train and for single attosecond pulse. So the black references here correspond to attosecond pulse train, And the technique used is called rabbit, like reconstruction of attosecond beating by interference of two-photon transition. And it's an interferometric technique which I will describe in detail later. And this was done by the group of Pierre Agostini in Saclay. And then in parallel, the group of Fehr and Cross, who at that time was at Vienna, showed that they could produce single attosecond pulses using very, very short laser pulses and using the streaking technique, which is a cross-correlation technique. This is a picture showing this first demonstration of attosecond pulse train with duration of 250 attoseconds. So what is attosecond science? And what is attosecond science at this conference? Attosecond science actually means several things. The first thing is really what I've been discussing so far, the interaction of an intense laser pulse, short laser pulse, with a system which is not only a simple atomic system, but even molecules or even solids. And looking at electrons or high-order harmonics or attosecond pulses. And there are actually many talks in this conference around this problem on atomic system by Nire Dudovic, Vasily Straikov, Alexander Bray, on molecular system by Valérie Blanchet and Hirohiko Kono, and on solids. This is really a new topic in attosecond science, which is very, very strong at the moment, by Mete Gorde and Misha Ivanov. So this type of attosecond science is called high harmonic spectroscopy, and the idea is to learn the physics of various systems looking at high-order harmonics or attosecond pulses. The second way to do attosecond pulses is to use these pulses that are generated, to move them, refocus them, and to use some kind of point probe technique using, for example, pulse train together with infrared field or single attosecond pulse together with infrared field, and looking at, again, trying to get information on this new information on the system, looking at electrons or looking at what is happening to the XUV light using transient absorption or emission techniques. And I think there are at least 4 talks in this conference which are related to this type of techniques, by a plenary talk by Joachim Burgdorfer and then by Giuseppe Sansone, Pascal Salière, and Renata Della Picca. You can ask, what else can you do? Well, you could do, in principle, attosecond pulse, attosecond probe. This is the holy grail of attosecond science. I would say, unfortunately, it's still very difficult using attosecond pulses from high-order harmonic generation in gas because, as you will see later, the process is not very efficient. So, but this has been realized using low-order harmonics, and it's of course realized, well, it's realized using femtosecond free electron laser pulse, and I think now there are attosecond pulse produced by free electron laser. So this attosecond pulse, attosecond probe is really coming up. Will be a lot in the next ICPIC. I just want to flash another way to do attosecond science, which we have beginning to explore in Lund, and which will be presented in a poster. And this is to use just a few controlled attosecond pulse, like 2 pulse. You can control the relative phase, or 3 pulse. Again, you know how to control the relative amplitude and phase, plus an infrared pulse. So this is an interesting new way to do attosecond science. So now I'm coming to the outline of this talk. First, I have give you a brief historical perspective and discuss what is attosecond science and what is going to be presented at this conference. So in my talk I will discuss, so this I'm using here the same structure as ICPIC. There will be no heavy particles, but photons and leptons, and it will be only electrons. Okay, so I will discuss photons, which means I will tell you what are the properties of these attosecond pulses that we generate. And then I will discuss electrons, how we can study photoionization of atoms and molecules in a different way using these attosecond pulses. But you will see that I will actually mix electrons and photons, both in this part and in the second part. So let's start by the first part. And I would like to come back to this three-step model and this intuitive picture of high-order harmonic generation or attosecond pulse generation. And this is a simple picture. And here is an exercise that I propose to all of my students at a master level, is to solve this equation. So this is the equation of, this is Newton's equation for an electron in the field. So this is the second step of this three-step process, this tunnel, and then this, the physics of high harmonics is very much determined by what happens in the continuum when the electron is moving away and coming back. And this can be very nicely described. Now my pointer is not working anymore. Yeah, it's fading. You can simply solve the Newton's equation using these initial conditions. It's a simple exercise. You calculate the trajectories, which are represented here. So this is the laser field, and these are the trajectories. And you see that depending on the ionization time, this initial condition, you can have electrons that move away. They contribute to ionization of the medium. They don't contribute to attosecond pulse generation. Thank you very much. I'll try to do that. Yes, it's better? Yeah. So these are this dashed line here. So the electrons don't move away like that. They move away like that. They oscillate in the laser field, but they move away. Now you have electrons that move away, but then come back. And you can calculate the recombination time, TR. So this is these trajectories. And you have short trajectories coming back very soon, and then longer trajectories coming back later. And you can calculate this recombination time and then calculate the kinetic energy of the electron at returns. And this is this curve, and it's really the basic curve of attosecond pulse generation. If you have to remember one physics results, it's really this curve. This curve shows the kinetic energy as a function of recombination time. This is in a cycle of the laser field, so this is really a short interval. And you see that you have the short trajectory here, and then the long trajectory. There is a maximum in energy. This is the cutoff of high-order harmonic generation. And you see that this also shows that all of these trajectories, of course, they don't come back exactly at the same time. If the harmonics were perfectly phase-locked, this curve would be like that, pang, just one peak. It's a little bit wide, and this kind of expresses the lack of synchronization of the harmonics. But still, it's a very good, it's a short time, and you have more or less short attosecond pulses. So you can express this cutoff with the help of what is called the ponderomotive energy, which is defined here. Depends on the amplitude of the electric field as well as the frequency of the laser field. And the ponderomotive energy is really a quantity which is used a lot in strong field physics, strong laser field physics, represents the wiggle energy of the electron in the laser field. Free electron in the laser field wiggle, and associated to that you have this wiggle energy or ponderomotive energy, which is proportional to the laser intensity and the square of the frequency. And the finding of these 3 points 17 UP was really a success of this model because the experimental result and the numerical result were showing this plateau and cutoff, and the dependence of this cutoff energy equal to 3.17 UP, more or less. Talking about uncertainty, 3 UP. So now I'm going from the electrons to the photons. So the property of the electron wave packets are then transmitted to the attosecond pulse. And the only thing I'm doing, I'm changing the scale from kinetic energy of the electron to XUV radiation frequency. And then I'm calling this recombination time, which is the recombination time of the electron, I'm calling emission time. This is the emission time of the given frequency components. And I get this curve, which goes now from the threshold, IP. This is IP divided by h bar. I'm in the frequency domain now, to this cutoff frequency, omega c. And I have this property that the difference between these two frequencies is proportional to the laser intensity. Okay, so now let's go a little bit deeper into what is the phase of this XUV radiation. So now this is a more recent result, a recent parameterization that we found that is actually very useful to discuss the properties of the attosecond pulses. So let's do a little bit of mathematics now. And let's consider only the short trajectory, which is the main trajectory which is actually observed in the experiment. We observe both the short and the long trajectory, but very often we only want to have the short trajectory, which has the best properties, and we tweak the system to have only the short trajectory. I will explain later how we do that, but let's forget the long trajectory, only consider the short trajectory. So what can we do? Well, first of all, as a physicist, you like to make Taylor expansion, right? So let's linearize this curve here. And it's actually very close to a straight line. It's this plateau. And, okay, so here I have the variation of omega as a function of time. You can actually invert that and talk about time or delay as a function of omega. This is a group delay in optics. So let's do that. And so I'm writing the equation of this straight line as time as a function of omega. And this is the equation of the straight line. I hope you follow me. Yes. I can integrate that. The integration of the group delay is the spectral phase. And I get a constant phase plus a group delay. Simply take the integral of this equation here, plus a term which depends on the square of this frequency difference, omega minus omega p square. And this looks very much like the expansion, which I'm sure those of you that take optics at the university recognize. This is the expansion of a spectral phase of a short laser pulse with the constant phase, a group delay, and then a group delay dispersion. And you know that the properties of your pulse is very much determined by the group delay dispersion, how big this is. This is very similar. The only difference is that we don't use the carrier frequency. It's much more convenient to use here the threshold frequency, omega p. So now let's focus a little bit on this term. This term, remember, I discussed that this difference here is proportional to the laser intensity, so I can write this term here as gamma divided by I. This term is proportional to the laser intensity, and the difference between Tc here and Tp, you can convince yourself very easily that it does not depend on intensity. When you change the intensity, what happens to this curve is just stretch towards the top, okay? But the position of Tp and Tc is not changing. This is moving up linearly with the intensity, and this does not change. So we have this parameterization here, and gamma, you can calculate gamma rather easily. This is the expression of gamma for a wavelength of 800 nanometer, which is the wavelength of titanium sapphire. So after this mathematics, we can do a little of the physics and what is the consequence of that. So I just rewrite this equation. You can immediately see that gamma is positive. You have a positive group delay dispersion of the attosecond pulse. This is an attosecond chirp, the radiation each chirp, which means that the frequency component do not arrive at the same time. There is a delay between the arrival of the different component. It's called also attochirp. Your attosecond pulse looks something like that. This is the picture you should have of attosecond pulse, something like that, with the red component, which means the low frequency components, arriving first, and then the blue component are a bit delayed. And this is again an expression for this, how good this phase locking of the high harmonics is. It's not perfectly good. There is this chirp, which you have here, but it's still okay. You can use the same expression to actually characterize the properties of the high order harmonics. So now you fixed one frequency, omega, and you looked at how this phase vary in time. So now I'm considering one single harmonic and examine the properties of the single harmonics. And this expression show you that this high order harmonics, the individual harmonics, have a chirp. You can stay in the temporal domain here and calculate the chirp, which is the double derivative of this expression with a minus sign. This is negative. The individual harmonics also have a chirp, which is negative. Okay, so now I have a little bit introduced the properties of the attosecond pulses and discussed the temporal properties, this structure in terms of pulse strain, and then the chirp of the attosecond pulse. Now let me discuss efficiency and versatility. What do I mean by that? And to that, I would like to say that this process is not only a process which can be described by single atom response. And this is, to me, this is what makes this really interesting physics, because it's not only atomic physics, it's also nonlinear optics. To understand completely the process, you have to consider the interaction of several atoms with the radiation and what happens, what is the response from a medium, and how you can optimize this response. So to get efficient high-order harmonic generation, you need to have a certain phase relationship between the emission from the individual atoms. This is usually described by Maxwell equation. So to describe completely this process, you need to combine Schrödinger equation. Do you hear me? Yes, okay. And this is described by a wave equation, which you can see here. I hope you recognize. You have a propagation term. Z is the propagation direction, this direction. You have a diffraction term, and you have a dispersion term here, coming from the fact that the refractive index depends on frequency. And then you have, of course, the source term of Maxwell equation, the nonlinear polarization of the medium. If I want to extract the physics out of that, how do we get efficient harmonic generation? You want to have the phase velocity of the harmonic field, which is created in the medium, equal to the phase velocity of the fundamental field, which is driving the process. This is what you want to have. Do we have that? Actually, no. In general, this is really wrong. And let me show you a picture from the book of David Atwood, showing the refractive index of a material as a function of frequency from visible to X-rays. And you have this variation of the refractive index with absorption edge here, different position. In general, almost all materials have a refractive index in the visible infrared region, which is larger than 1. In the XUV, below than 1. And this is where we are. This is where our fundamental is, infrared region. This is where our high harmonics are, in the XUV region. So this can, in principle, never be achieved. Except, so now I'm writing the expansion of the refractive index of the fundamental. This is for neutral medium. Fortunately, in this process, you ionize the medium at the same time. These are the trajectories that just go away. They contribute to ionization and to free electrons in your atomic medium. And these free electrons, this is like a plasma, a dilute plasma. This electron will contribute, will modify the refractive index for the fundamental field. It's adding a term which can be written as something like that. This is the density of free electrons. And so it lowers the refractive index to below 1 so that this can be achieved. So this is more or less the physics of phase matching of high order harmonics. In reality, it's a little bit more complicated than what I said. You have 4 contributions. This is a little bit more advanced phase matching. You have here expressed in terms of wave vector mismatches, a little bit similar to what you do when you work with nonlinear crystals for second harmonic generation. You talk about delta K. For this process of high order harmonic generation, you have actually 4 terms. Neutral contribution, free electron contribution, this is what I just discussed. In addition, you have also the effect of focusing, adding a GUI phase, and also the effect of the spectral phase, which I discussed previously, which I repeat here. And now for this problem, what counts is the Z dependence of the intensity here, the Z dependence of the phase, which contribute to a phase mismatch. So you have here different signs. You can also see that this contribution depends on the sign of Z, which before the focus or after the focus, so also leads to an asymmetry in this process. You have different conditions if you generate your harmonics before the laser focus, or at the laser focus, or after the laser focus. In addition, to really understand completely this macroscopic aspect of high-order harmonic generation, you of course need to include the influence of absorption or ionization, if you want, that also limit the efficiency that you can get. So in this plot, I kind of summarize what has been achieved. It's a little bit difficult plot, so I try to be try to explain what it is. So this represents several results. The points are experimental results obtained in the whole world. I think this field now is getting really quite big. So in color, you have the photon energies. So you have a blue color. This means you generate in argon gas around 30, 40 eV. And then you have green. You generate neon around 100 eV, up to 100 eV. And then you have this brown color, which represents harmonic generation with photon energy in the kilo electron volt. This is really very, very difficult and requires, I will mention that later, other type of laser with longer wavelengths. What you have here is the energy out per pulse, so up to 1 microjoule. We are behind, of course, what you can do with free electron laser. This is a rather low efficiency source. on the horizontal axis, you have the repetition rate of the source, which is the repetition rate of the laser that you use to generate the harmonics. So you see that it can vary from hertz to actually gigahertz. And if I plot instead the input energy, the laser energy, roughly you have 1 joule to 1 nanojoule here, microjoule, millijoule. So this plot tells you that this source is incredibly versatile. You can use very high repetition rate, low energy driver, and get attosecond pulse. Of course, they will not be very energetic, but they will have a very high average power. Or you can use high energy driver, of course, low repetition rate, and get microjoule and maybe higher, a few microjoule. The efficiency, the fact that all of these points are more or less along this diagonal, tells you that the efficiency is more or less constant. It's about 10 minus 5 for the blue region, 10 minus 7 for the green region. So this conversion efficiency does not change much for a certain photon energy range. So what is the reason for this versatility of the attosecond sources and for this kind of constant conversion efficiency? It's a little bit frustrating because of course you would like to increase the conversion efficiency, but somehow it's very difficult. So what is the reason for that? Well, there is a geometrical scaling principle that I'm going to try to explain to you. This is again this wave equation which I wrote before. So now let's do a little bit of mathematics. Let's multiply z by eta square, certain coefficient eta square. You see that this is getting multiplied by 1 over eta square. Then I multiply r. This is the radial coordinate. You can think of x and y if you want, by eta. This term, this is the Laplacian in the x and y direction, will be multiplied by 1 over eta square. Let's assume that the pressure, let's scale the pressure by the same 1 over eta square factor. So this term will be proportional to 1 over eta square. And this term, the nonlinear polarization, is proportional to the pressure, will also scale as 1 over eta square. So this shows that this wave equation is really invariant, completely invariant, strictly invariant if you multiply z and r by eta square and eta, and then at the same time you apply the scaling factor for the pressure. So you have the same thing and the same conversion efficiency if you use low energy, certain pressure, certain length of the medium, a certain radius, as if you use much higher energy, much lower pressure, a longer length, a longer radius, but you scale all of these parameters according to this picture, and you get eta square, the energy, the output energy. So it's a very basic and very fundamental scaling property that really explain, I think, the diversity of this harmonic source, which with a variation of 10,000. You can't imagine have a free electron laser, which you have here, and then the same 10,000 longer and bigger. It's the same size. Harmonic generation, you can have very compact system, and then a big system delivering 10,000 more photons. Of course, at a 10,000 repetition rate less. So just to show you a picture of what do they look like, these attosecond sources, I show you a very compact system using a laser, which is an optical parametric Chirper amplification system. 10 microjoule energy, this is very little. 200 kilohertz repetition rate, it's a lot for this type of physics. CP stable, this is the laser system, it's very compact. It's in these 3 boxes. This is the attosecond sources, it's that big. And this type of system are very interesting for condensed matter applications. And AMO science, where you would like to detect, for example, electron and ions in coincidence using a cold TRIMS. You have here a picture of the cold TRIM setup, which was built in Lund. So this type of system, many attosecond pulses, high repetition rate, low energy per pulse. This is a picture of a system in the other direction, where you want to have many photons per pulse. This is the intense attosecond source at the Lund Laser Center. This looks very much like the beamline at a synchrotron radiation. It's about 15 meters long. The laser is coming from a hole in the wall here, and this is your attosecond beamline. Here you want to maximize the photon flux. You use loose focusing geometry, and here you generate harmonics, and then you have 6 more meters afterwards to let the beam expand, and then to use the radiation for application. Just for making a little advertisement here, at this very moment, there is a big facility called Eli Attosecond in Hungary, which is being built, and which will have several attosecond sources really optimized using extremely good laser performances and hopefully good attosecond sources behind the laser for user. So it's really an attempt to provide to a user from the whole world a very nice XUV attosecond sources. Versatile attosecond source. What else can we say? I have described this geometrical scaling of the sources, which is really pure geometrical. There is also a wavelength scaling, which is in this expression here. The cutoff energy is proportional to the intensity and to the frequency square. So you see that if I increase the wavelength square, if I increase the wavelength, then this cutoff energy is increasing quadratically. And if you use infrared wavelengths, as showed in this picture from the group of Henry Kapteyn and Margaret Murnane, you can see that you can get photon energies up to almost or more than 1 kilo electron volt. So this is really a way to push this attosecond science into the X-ray regime. More versatility. Normally, you use linear polarized laser field to generate linearly polarized attosecond pulses if you use atomic system for the generation. But you can also produce attosecond pulse with circular elliptical polarization using tricks. If you use circular polarized laser, you will never get attosecond pulse because the electron is not coming back to the nucleus. So you will not have attosecond pulse. But you can use tricks, and there are several ways. You can use 2 color fields with different state of polarization. You can use a traditional way to produce circular polarized radiation, which is to split the pulse and then to recombine that with a change of phase. This will be described. I'm not going to describe these techniques. It will be beautifully described by Carlos Hernandez Garcia in his talk at ICPIC. You can also produce HAG and attosecond pulses with orbital angular momentum, which is also a new trend in this field to explore the generation of field with strange orbital angular momentum. So let me, now I'm a little bit lost, where I am in my talk. Okay, so let me conclude by describing a little bit the spatial properties of the high harmonics or attosecond pulses. I'm starting with Gaussian optics. I hope most of you know this picture. This simply represents the characteristic of a Gaussian pulse across the focus with a certain wavefront and radius as a function of z. So what happens when you generate high harmonics? What are the properties of the spatial properties of this harmonics? So now I'm considering one harmonics q. So big omega is equal to q omega. And I'm looking at the phase of the high harmonics. Of course, you have the phase which comes from the fundamental, which is q times phi of z. But you have this contribution from the spectral phase, which I have discussed already a lot with you. So this is the spectral phase inherent to the process, which is accumulated by the electron in its trajectory in the continuum and then transferred to the photon. So what is this spectral phase? Now I write again this parameterization of the phase. Now what matters now is the R and Z dependence of the intensity, which, making a Taylor expansion here, I see that you have a contribution to the wavefront. I have an R squared term to the intensity contributing to the wavefront of the high harmonics. And this is the calculation of the wavefront of the high harmonics. You have one contribution, which is in black here. This is the contribution from the fundamental. And then you have another contribution, which is actually constant, using this parameterization, and which is in green, and which is divergent. So the contribution from the fundamental is conversion, and then divergent as you go away from the focus. This contribution from the electrons is only divergence. It's actually constant through the focus. So now you can add in your head these two contributions. What will you get? Well, of course, it depends on the relative strengths of these two terms. And you have, depending on where you generate harmonics, you can have, for example, here you have still, the sum of this is still a conversion beam. So you have a generation of convergent harmonics, and maybe they are converging actually past the focus of the infrared. So you focus your harmonic long after the infrared photon. Or you can generate harmonic, for example, here, approximately at the focus of the infrared field, and you will have a focus of the harmonics which is actually before, so it's a virtual focus, and you have divergent harmonics. If I consider several harmonics, your attosecond pulses, then it can be quite complicated. This is a picture of the case where you generate your harmonics before the infrared photons, and the different colors represent the divergent property of the different harmonics. So think about these different harmonics making your attosecond pulses. Some of them are focused before, and some of them are focused after. And this is making your attosecond pulse. So quite complicated focusing properties, right? This has an expression in optics. It's called chromatic aberration. You have very different spatial properties depending on the frequency. Chromatic aberration, or if you go from frequency to time, this is also called spatio-temporal couplings. Your pulses have a strong spatio-temporal couplings, which means you cannot approximate your electric field as a product of a spatial field and a temporal field, as you do normally in all optics book. You do this approximation, spatial properties and then the temporal properties. You really cannot do that for attosecond pulse. And this actually asks the question, I can ask the question to you, can we focus attosecond pulses? If you want to do attosecond pulse, attosecond probe, which means you need some intensity in this radiation, you need to focus the attosecond pulse on a small spot in order to have a high intensity. So if you have something like that, then you have, can you see that it's below the computer, or you can see it? You can see it? Yeah? I can do that? Oh, no, it doesn't help. You have a very elongated focus. It's very similar. This is the translation of the temporal properties to the spatial properties. In temporal properties, you have this chirp. The different frequency component arrive at different time. It's not too bad. It's still attosecond, but still it's different. And here, the attosecond pulses are focused actually at different position, depending on the frequency component. So you have an elongated focus. And this might be the reason why it's so difficult to get attosecond pulse, attosecond probe type of experiment to work. People have tried that since 20 years, and a few have managed with low order harmonics, but it's still more difficult than it should be if you just consider the intensity of the radiation. So this is something to work on. So to summarize this first part, I have explained to you that if you focus femtosecond laser pulse in a gas, you get a train of attosecond pulses. In the frequency domain, this is equivalent to a spectrum of high-order harmonics. Of course, you can select one of these pulses, or actually generate only one pulse using very short laser pulse, or alternatively you can use polarization techniques, which I don't have time to go into. And of course you get a broad pulse, broad frequency. You can also select one harmonics. In the time domain you will get, of course, a longer pulse, approximately the same duration as your input pulse. Or you can use actually the train of attosecond pulse. You can use the frequency comb of high-order harmonics. I have told you that the temporal and spatial properties are determined very much by the intensity-dependent spectral phase of this radiation, which is mainly due to this second step of the three-step model, the electron propagation in the continuum. So remember this figure. And finally, I have tried to explain to you that this is phase-match radiation, it's nonlinear optics, it's propagation along a certain axis. It's not very efficient, it's extremely versatile, which I think is an interesting property of this source. And the reason for the versatility is, at least for the geometric, is due to this scaling principle, as well, of course, as the versatility of the driving lasers. During many, many years, we have used only the titanium sapphire laser to generate harmonics and attosecond pulse. The last 5 years, there is really a lot of new laser systems that are used based on ytterbium, optical parametric amplifiers, many, many type of system. And this is really changing the landscape of attosecond pulses, and this is a very recent development. So now I'm moving to the second part of this talk, which is leptons, or electrons, if you want. And here I will try to explain to you how we use these pulses to study photoionization, maybe in a new way compared to using synchrotron radiation. And I will start by actually telling you how do we measure this attosecond pulse. So I'm mixing a little bit photons and electrons here. How do we measure attosecond pulses? The idea is to use atoms as a nonlinear medium to expose atoms to a train or a single attosecond pulses that you want to determine a probe field, and then to look at electrons. And in this idea, we assume that the electrons are a replica of the photons, which is of course not true, but I will discuss that later on. So let's assume for a little while that your electron wave packets here are a good replica of the attosecond pulse that we want to measure. So what are the methods? The first method, which is used for single attosecond pulse, is the so-called streaking technique. It's a cross-correlation technique. You expose an atom to your single attosecond pulse and the infrared laser pulse, which is used for the generation, and you record the photoelectron spectra. And you see this streaking trace here, or this is another result by the group. This is from the group of Garching, and this is from the group of Mauro Nisoli in Milan. And what happens here is that the infrared field is giving extra energy, extra momentum to the electron, which is moved in the continuum by the XUV laser pulse, and resulting in this streaking of the momentum distribution of the electron. I think this will be described in detail by Joachim Bürdorfer in his talk, so I'm not going to say much more. I would like to concentrate on the Rabi technique, which is an interferometric technique, which I like very much, I must say. And so this technique, here we want to characterize a train of pulses in the frequency domain, high-order harmonic frequency spectrum. Same idea in a gas, looking at the photoelectron spectrum. So if you just ionize your gas with this radiation, you get electrons at given energy, at given energies, and separated by twice the laser frequency. But now if you mixed with a weak fraction of the infrared field which is used for the generation, represented here in the frequency domain and here in the time domain, you have even two photon processes leading to the generation of sideband peaks that you see here. And what is interesting here is that a given sideband state here can be reached by two paths. One path with absorption of this harmonic and this infrared photon, and one path with absorption of the next harmonic and emission of an infrared photon. So this is a quantum interferometer. And as soon as you have an interferometer, you think, oh, phase measurement. And the idea here is, oh, but this signal here carries information on the phase of this harmonic and the phase of the next harmonic. So we have information which depends on the difference between the phase of two consecutive harmonics. Of course, when you have an interferometer, you need something to vary because you want to detect fringes. And what we vary here is the time delay between the infrared field and the train of attosecond pulses. And this is done in an optical interferometer. This is the one used in Lund. You have many variants of interferometer in the different labs. Here it's a Mach-Zehnder interferometer with a pump arm. So you have the laser here being focused in a cell, producing a pulse train. The fundamental pulse is filtered out by a metallic filter, and this is simply a delay line for the weak fraction of the infrared field. And then both pulses are focused into a medium with a gas, and this is an electron spectrometer, and during the next 10 minutes I will discuss angular integrated measurements obtained here using a magnetic bottle electron spectrometer, and this is a collaboration with Raymond Feifel and Richard Quip in Gothenburg. So this is a typical rabbit trace where you see the photoelectron spectrum here in color as a function of energy. Here I only represent the orders. You have the peaks due to absorption of the harmonics, and then in between, this is the interesting information. This is the sideband peaks as a function of delay, and you see this very nice oscillation of these sideband peaks. So this is your interference signal. The interesting property is included in this phase of the sideband, and how this phase vary from one sideband to the next, how it varies spectrally over your spectrum. And again, assuming that our electron wave packet is a good replica of the attosecond pulse, you can determine from this phase difference the group delay of the attosecond pulse, or this is the variation of the spectral phase of the attosecond pulses. This is an example of result, and here I'm also writing again this expression, the derivative of the spectral phase, which I have shown many times in this talk. Remember, I just take the derivative of the square term here, and this is your spectral variation of the spectral phase. And this is an example of experimental results. You see that indeed this group delay varies quite linearly. This is my first linear approximation that I made at the beginning of this course. It's actually quite valid as a function of harmonic order. And if you know the derivative of the spectral phase and the intensity of the radiation, which is sample, of course, at the harmonic frequency, but you have a good sample of the intensity of your attosecond pulse. You know the derivative of the spectral phase, which means that you know the spectral phase within an absolute phase, which we don't care. So if you know that, you know your spectral amplitude of the radiation field. You can do a Fourier transform, and you know completely the electric field of your radiation. Okay, now let's go a little bit in more detail about this rabbit technique. So now I'm going to be a little bit more mathematical and more lecture type, okay? And I'm going to do second order perturbation theory, quantum mechanics. So I have a slide here with equation. Basic equation of the rabbit technique. How do you do that? Well, you take the sum of an absorption term here, plus what I call emission term, this is this process, square. You square amplitude, not intensities. So you have the square of these two terms plus the interesting cross product here. Okay, and what is the expression for this transition? This is the expression using lowest order perturbation theory. I hope you recognize that. Do you? Yes. Within the dipole approximation. And you see that you have some atomic quantities. You sum here over intermediate states, and you have the field which are used, the fundamental field and the harmonic field. Let's look at the phase of this term. What do you have? Well, you have a phase due to the fundamental field. Remember, the fundamental field is delayed compared to the attosecond pulse strain by a quantity which I call tau. So you have omega tau here. I assume otherwise it's a perfect field, so it's just omega tau. And then you have the phase of the acute harmonic. This is my spectral phase, which I'm discussing all the time. Okay, what is that? I write a third term here. Where does it come from? I need you to interact a little more now here. It's come from this, right? Yeah. Why does this thing has a phase? Why is it complex quantity? Yes, exactly. It's because this is in the continuum. If this was in the discrete spectrum, this would be only real. So it's in the continuum. So this time there is a pole here, and this can be described by a complex quantity. So this term here is coming from the fact that you are in the continuum. What is the phase of the second term? Now we have the complex. This is an emission process, so it's a complex conjugate of E1. So it's minus omega t, plus same thing. Spectral phase of the Q plus 2 harmonic, and then the spectral phase coming from this term here for the emission process. Okay, now I make the difference. What do I get? I get 2 omega tau plus the difference here, plus the difference here. I can write this in the form of delays, where this is the group delay of the attosecond pulses. This is what I have discussed already. And here you see that what is measured in the Rabbit technique is actually a finite difference approximation of the spectral phase. There is also an atomic delay, which I'm calling atomic delay, meaning that it is related to the atoms, which is this term. This brings me to the second part of this last chapter, photoionization time delay. Showing this slide again. Now we're changing this point of view. We are not interested in the attosecond pulse characterization, but actually, what is this atomic delay? And we're interested now in the photoionization process. So we know now that this electronic wave packet is not simply a replica. It also carries information about the ionization process. We have this expression now here. So let's look at this tau A, the problem. You see immediately the problem. When you do a measurement, you have the sum of two terms. How can you distinguish? You can do difference measurements. And the first experiments were actually exactly that. This is the first experiment using the streaking technique performed by the group of Garching, and ionizing at the same time neon in the 2s shell and 2p shell. The outer shell is n equal 2, and you have 2s and 2p. And getting at the same time this spectrum, and you see that, well, I don't know if you see it, maybe you see if you are far away, but there is a slight shift between the two streaking traces. And the difference was measured to be 21 plus or minus 5 attosecond. Did not agree with the theoretical calculation which predicted 8 attosecond, which was actually a big puzzle during many, many years. Second experiment, and I think Joachim Berdorfer will discuss that in more detail. Second experiment, which I'm calling double rabbit. Similar idea. We ionize at the same time here argon atoms in the 3s and the 3p shell, and look at the electron spectrum. Difference is we use a rabbit technique, so we don't see a spectrum looking like that. We see sidebands. And here we look at where is the position of the sidebands and how do they vary between 3p and 3s, of course, for the same sidebands, which means for the same attosecond pulses. And I don't know if you see anything, so I'm going to help you. I do like that. And there is a small offset between the sidebands here, and for the 3s, of course, the signal here is very noisy because the ionization cross-section in the 3s shell is much lower. but still you can see the oscillations. And the difference between 3p and 3s is 100 attosecond here. Now I ask you the following. If you think about it, forget this slide. Which one is ionized first? I'm talking about time now, which is very exciting when you do quantum mechanics. So I'm going to discuss this concept of time a bit later. But if you think about ionization, this is very fundamental, photoelectric effect. You ionize with the same pulse, same frequency, argon atom in the 3p and in the 3s shell. Which one is coming first? This is what we're talking about. What do you think? You have the answer here, but don't look at this. Think physically. And why? Actually, the difference is very, very small, so maybe you can simply consider they come at the same time, which is actually a good answer. No difference. Yeah. Actually, the P is a little bit delayed. Why is that? Compared to S. You could think, now I'm going to answer two different ways. You can think that the 2S is actually deeper, okay? So you could think that actually the 2p is coming first, simply because it's less bound, yeah? But there is also angular momentum barrier for p, which is higher than for s. So maybe this compensates, I don't know. Now I'm just speculating, but... Okay, so now let me show you go a little bit more in the detail of these experiments, and I'm not going to show details of these first experiments. This is very hot topic now in attosecond science. I'm going to show recent results, which we obtained in Lund for neon in the 2s and 2p scale using this double rabbit technique, with the idea to try to understand the discrepancy between theory and experiment in the first Garching experiment. So this is the scheme. We ionize neon in 2s and 2p shell at the same time. Now, this is obtained with a very small spectrum with only 3 harmonics, and this means that we can really distinguish between the 2s and 2p ionization, and you have a good precision in the measurement of the phase offset of the sidebands. And so this is the sidebands varies with an offset depending on this, and which means that we can take the difference. And this is the result. The blue points obtained with this very small spectrum. And this is the Garching result. So we first obtained the 2 points and then these points. And we said, we have to take more data. So then we used this much broader spectrum and obtained these points, which really agrees with the theory. And this is collaboration with Eva Lindroth and Marcus Dahlström. So why do we have a difference here? Well, the difference is that we have a much better spectral resolution in our rabbit measurement compared to the streaking measurements which use single attosecond pulse. And here it's very interesting because I'm talking about high temporal resolution, of course, but I want to keep a high spectral resolution. Is it possible? I should hear only one response here. No! Of course, no, it's not possible. But yes, it is possible. We are a little bit circumventing here Heisenberg principle. The reason is that we are using, actually, many measurements. We are using a long pulse train, so we are not violating anything. I'm just reassuring you. But it's a way to actually perform experiments with high spectral and temporal resolution. So our resolution in this experiment is limited by the harmonic bandwidths and not by the attosecond bandwidths. And this is the trick. So what happens and what is the difference between the two measurements? we think that very close in this energy region, you also have shake-up processes where you ionize electron in the 2p shell and then move 2p electron to 3p electron. It's very close in the energy region. And you can see here in this example, here the position of the sideband due to 2s ionization is very close to the position of the absorption of harmonic 61 for the shake-up process. And of course, we need to disentangle the two processes in order to do a good phase measurement. And to do that, we use a kind of variation of the rabbit technique, which is called rainbow rabbit, which is introduced by Pascal Salière and his group and will be discussed in his talk. We spectrally resolve this phase variation within the electron peak, as you've seen here. You can see that you have a certain phase variation in black. For this sideband, this is what I'm interested, and here a difference phase variation. If I integrate over this peak, I will do a wrong measurement. I will not measure the correct phase. So we think that is the reason for the different measurement compared to the streaking method, that we could get rid of this shake-up process and perform a more spectrally resolved measurement. Okay, so now let me discuss a little bit this method. So let's go a little bit deeper into quantum mechanics and atomic physics. This is what we discuss. So now, okay, let me start again. Now I want to give you an interpretation for this atomic delay. What is this atomic delay? So let's look again at this two-photon process. And actually, I can now write this atomic phase as a sum of actually two terms. One, which is the scattering phase of this state here, this intermediate state, eta lambda. Lambda is the angular momentum for this state. So this is one photon ionization. And then you have a term here, which I call phi cc, corresponding to this second step in the continuum. This continuum is called phi cc as continuum-continuum transition. Let's look at the emission term. Same thing, you have a contribution from the one photon process. This is the scattering phase of this term here, or the one photon ionization phase of this term here. And then you have this contribution from this continuum-continuum transition. So I can do the same mathematics. I take the difference, and then I get two terms which make this atomic delay a term which is called the Wigner delay, and then this contribution from this continuum-continuum transition. So this allows me to really interpret now what we are measuring. There is one contribution, which is the Wigner delay, actually introduced by Wigner in 1955. This is the spectral derivative of the scattering phase. Physical interpretation, it's the group delay of the electron wave packet created by absorption of attosecond parts as it propagates in the potential. This group delay is the derivative of the scattering phase, which represents the difference between the phase of the outgoing electron at a given energy relative to the phase of a free electron at the same energy. And then you have a continuum-continuum contribution, which comes from this interferometric measurement. You need to make the two arms of the interferometer come together in order to do your interferometric measurement. So you can consider this as a measurement, a correction due to the measurement, which is a nice concept in quantum mechanics. So this is a measurement quantity. Fortunately, this continuum contribution is very universal. This is a calculation performed by Richard Tayeb and his group I think in hydrogen for different momentum channel, and you see that they are more or less on the same, they coincide, and it's largely universal. It is equivalent to another quantity which has been called Coulomb laser correction by the group of Joachim Bergdorfer. It's the same quantity. And if you want to have more detail, you can look at these references. This is another view of what is this time delay, Wigner delay, more like collision, which should be the case at peak. And it's a picture from the very nice article by Luca Argenti and co-workers. This shows you the electron wave packet, free electron wave packet, and electron wave packet going through a potential. And what is measured here is the delay between the two electron wave packets, or the Wigner time delay. And it's the derivative of the spectral phase. In our problem, we just consider photoionization, which is half of this process, half this collision type of process. What happens if we have two angular channels? Can this apply? What do you think? We're a little bit lucky here, because remember, we are doing angular integrated measurement. And the signal, with the sideband signal, can be written as the sum, incoherent sum of two terms corresponding to two final momentum, D or S, as you can see here. Why can we do that? This is simply because we do an angle integrated measurement. We integrate over the solid angle. We integrate the product of two spherical harmonics which are orthogonal to each other. So this is why you have no cross term and you have this incoherent sum. The phase, so we have two rabbits here. Two incoherent rabbits. How can I measure phase? You can measure phase if this phase is the same for the two terms. And this is the case, because we just showed that the first term only depends on the intermediate state here. It only depends on the one photon ionization step. And the second step, the second term is universal, does not depend on angular momentum. So these two rabbits are in phase. So that's fine. What happens when we have multiple angular channels? This is for 2p, m equals 0. You have also m equal plus or minus 1. It's getting complicated. And this is only neon. So how can we do that on big molecule or things like that? Well, this is what we have. Now I'm writing here the m state and the final state. So you have these four terms, which you add incoherently. Does it work? What do you think? This is basic atomic physics, right? There's only one answer, so no. It doesn't work, because you can see there are two different intermediate, you have two different scattering phase here, which are not the same. So these three are the same, because you have only, you only go through the D state here. But this one includes this channel and this channel. So in principle, this should oscillate out of phase. Fortunately, in most of the case, the D channel is the dominant one, even for this one. So maybe we can forget about this path here. But you see difficulties here. Okay, I think I should speed up. How can we disentangle the different channel contribution? You can do angular resolution, which also brings some additional difficulty, which I wanted to discuss a little bit, but I think I will stop. And you can also change the polarization state of your radiation. So I had a last topic, which was to maybe discuss a little bit a few current topics, but I think I will finish. So yes, so I summarize. What we're trying to do with this Attosecond science using rabbit or streaking techniques, looking at photoionization of atoms, is really to look. We are not doing the same as was done previously with synchrotron radiation. This is a beautiful result by Madeleine, Ederer, and Kodling, 73 in argon. This is the same range as what I am discussing, 20, 30, 40 eV. We are looking at the same processes, ionization in 3p or in 3s. We are also looking at, we can also look at auto-ionizing states. I didn't have time to discuss that. So, but what we're trying to do is really to look at this, all of these processes in the complex plane. We are not measuring just the amplitude, we are measuring the phase. If we know a process, the amplitude and phase, then you know everything. You know the probability amplitude in the complex domain, and you can recover the dynamics of the process. People talk about Attosecond physics, say, oh, we can measure electron moving. I like much better to say, oh, we are measuring amplitude and phase. This is the strength of Attosecond science. We measure amplitude of phase of quantum mechanical process, and we can really recover the dynamics of this process. I think I will stop here. I would like to thank many people, many collaboration with theorists, Eva Lindroth, Fernando Martin, and this is a picture of the group in Lund. Some of them are here at this conference. Thank you very much.
Thank you very much for this very pedagogical presentation. So I think we have time for a few questions. If lunch is maybe it's late for the French standards, no, it's okay. Okay. Yeah, please.
Thank you very much, and it was an interesting talk, especially for the second time delay. But I think if you want to expand this kind of study to molecule, especially for complex molecule with lower symmetry, like say a biomolecule or whatever, in that case we cannot restrict symmetry. What happened?
This is a very. Can I repeat? I repeat the question. Can you extend this type of investigation in more complex system like molecule, in particular for where you have many symmetries? I think you have to look. You have to look at each case separately. And yes, you can do this thing on molecule. We have a very nice project with Fernando at the moment in N2 molecule. I would like to say that one trick is really to push and push and push the spectral resolution. This looks anti-Heisenberg. How can we do that? But yes, we can do that because we use this Attosecond pulse train, which is very long, right? So we can have a nice spectral resolution. So push the spectral resolution and of course get the momentum, the complete momentum picture. So I think we have to go step by step, atoms, small molecules, and big molecules. And I'm sure you can do many things.
Okay, thank you very much.
Yeah, it's a very nice talk. I really enjoy it. But I have a question on the page 32 that you showed the streaking phenomena.
I try to do that.
Maybe
No.
32.
Yes.
Yes, 32. Yes. Maybe.
No. Okay. I
Okay.
can't do. Doesn't
I
work.
can just express my question like this. When there is a streaking phenomena, of course there are some modulations, energies are just jumping up and down. But normally before, you see, before the streaking happen and after streaking happen, the intensity is always much more intense than when it happens. You see, it's very weak in the middle. There is some reason for this, or just artifact by the eye?
You mean the variation here on the side?
Yeah, this looks very intense, right?
This is the photoelectron spectrum.
Yes, yes.
And here you have a photoelectron. You have a spectrum which is broad because it's a single attosecond pulse.
Yeah. What I say, intensity at here is very high, and in the middle you have this string, and the intensity looks lower, right?
I think because simply you redistribute your. I think if you integrate this in energy, you will get more or less the same spectrum.
The same.
It's kind of stretched or streaked. This is the right word. It's streaked in energy.
I see.
It's yeah.
Thanks for the next talk. I have a question about long trajectory and short trajectory. Why the short trajectory is dominated? Because it's phase matching, or?
Yeah, it's a very, very good question. I can spend an hour on that. But I will give you actually two answers. One is here, it's phase matching. You have a term here which depends on the electron. This depends on the electron trajectory. This is only for the short. So this term here depends on the electron trajectory. So they are not really phase match in the same condition. The second answer I want to give is here because I think both contribute. It's in this plot. It's the short and long trajectory have very, very different divergence property. So again, this term is different for the long trajectory. So in general, when you have this, if I move to the next slide, here you have very well collimated harmonics. This is the short trajectory, and here as well. If you consider the long trajectory contribution in this region will be highly divergent, very small focus because of the strong phase variation. So very small virtual focus and highly divergent beam. So I think the beam is simply diverging. So it's the second answer. This is why we see it. So it's enough with a diaphragm somewhere in your beamline to cut most of the long trajectory. So that's my two answers.
Any more questions?
Thank you. It is an old story now, but I have the feeling that you are quite pessimistic about the efficiency. It is about the application of harmonic generation to do nonlinear physics. I mean, to photon ionization or things like that. Do you think there is a hope for such an application? I would say in a systematic way.
Okay, I think maybe I am a little bit pessimistic. I'm just trying to be realistic, actually. But so no, let's maybe be a little bit more optimistic. First of all, even if the conversion efficiency has not really increased the last 10 years and so, there are techniques using two color fields, and you're welcome to have new ideas. Here is something really to do. Boost up the conversion efficiency, and this is really good. But it's difficult. But what you can do is scale up your source, and the lasers are really progressing. And I think the Attosecond sources that are being built at the moment at this Attosecond source at Eli should have a much higher energy per pulse, not better conversion efficiency, but more flux with, in addition, very good repetition rate. So my hope is with the new, the future sources at Eli, we can really do a pump probe experiment, Atto pump probe. So I'm not, maybe I sounded a little bit pessimistic, but I'm not, but it's simply more difficult, but can be done. Yes.
Any more questions? No, oh yeah, another one.
Regarding the HHG process, I have a question. If we are generating the HHG, the harmonics, by only changing the position of the generating medium before the focus or in the focus or after the focus, how do these three XUV spectrum differ from each other? Is it possible to distinguish them, or just looking at the XUV spectrum that we are measuring is in front of us?
You mean how can I distinguish if I generate before or after? Or
Yeah.
Well, in some condition, first of all, you do see the long trajectory. So this tells you a little bit where you are, probably very close to the focus. And again, the divergence property of the harmonics are different. So they are, if you are before the focus, they are very well collimated. If you are after, they are more divergent. So this is how you can distinguish. I would like to say that this divergence measurement and this understanding of the divergent properties are very new. It's only a couple of years, and by several groups, by our group and by the group of Bordeaux in France, Eric Constant, Eric Mevel, and also a group of Paul Corkum a little bit earlier. So what I want to say here is that this is a process that was discovered 30 years ago. We're still learning new things about it, which also show the richness of this process. How interesting is it? So this is also something I want to tell you. You can think, oh, this is a source, we know everything about it and we use it. There is still a lot to do about the source. We need to make it more efficient. We need to make it more controlled. And we need to focus it the way we want to do that. There's really a lot of, I think, room for creativity for young people like you. Yes.
Yeah, just a very short one because I think people are hungry now.
Okay, thanks a lot. So why don't you see the future of Attosecond pulse generation in laser plasma wake field acceleration? Because you can get a higher efficiency and shorter pulses.
This is a very good question. I haven't discussed at all other type of Attosecond pulses. For example, Attosecond pulse sources obtained by other mechanism in strong laser field, like wake field acceleration. I don't know actually about wake field, but this relativistic plasma mirrors. And I think these sources needs to progress a little bit in usability, I would like to say, to be really used for applications. I think they are progressing. You have a better efficiency, but you need a really very intense and high energy, high power laser. The laser I'm discussing are small. So I think that's the difference. But I think this is also coming up. And at this Eli facility, you will have Attosecond pulses generated by like plasma relativistic mirrors. Yes.
Thank you.
Okay, I think we should stop here and thank Anne again.
Okay.